again, what are we talking about? So curves have what's called curvature, and it's kind of like the tightness of the turn, right? The tightness of the turn. So now the curvature is high or low right now. And now it's high or low? Low curvature. What about now? High curvature through here. And then low curvature, right? So when curves are more straight, the curvature is low. When there's a tight twisting turn, curvature is high. Okay? So let's... So then, mathematically, it's basically dt ds. And what was t again? Unit tangent. So dt ds, we're talking about the what? The rate of change of what? Rate of change of what? T is a unit tangent. It's always got a length of 1. Yeah, so that's change in direction, right? If the magnitude of t is always 1, then the change in t would be how much turn, and that's per ds would be unit of arc length. So it's how much turn you get per distance traveled. So that makes sense, right? So if you get a lot of turn for some distance traveled, then your curvature's higher. All right? So it's the rate of change of direction with respect to arc length. That's what we're talking about, dt ds. And so that could also be t prime divided by r prime. Because t prime would be what? The rate of change of direction with respect to the magnitude of r prime would be how much distance covered per time. So we can calculate curvature with r prime and r double prime. So the question is, would that be a matter of the dot product of r prime and r double prime, or the cross product of r prime and r double prime? So what is r prime? R prime is like... Someone said velocity, right? This is velocity. If r is position, then r prime is velocity. And then r double prime is acceleration. So, would we want dot product of those two things, or would we want cross product of those two things if we're talking about curvature? Lots of you saying cross product, which is correct, right? Dot product would be how much those two are in the same direction, right? We talked about our concept of dot product. Cross product is kind of the product of the magnitudes in as much as they are orthogonal, right? And that would have to do with curvature, right? We want orthogonal to r prime, not in the direction of r prime, right? So this is a formula for curvature, and you had a variation on this in your web work. Is equivalent to this. So something had to do with like f double prime and g prime and all that stuff. Like if you had parameterized a two-dimensional vector parameterized. But here's a more general formula like the one that you used in web work. So really, we don't really use these to calculate curvature. These up here, we don't really. This is more the concept of it, right? Rate of change of direction with respect to how far you go. It should make sense that gives you curvature. Now we're talking about actually calculating curvature. Here's a generic formula, and that works for a two-dimensional vector or a three-dimensional vector. Doesn't matter. That will work for both. Okay, and then in R2, if you have y as a function of x, I should say, let's go. That becomes this, and so this is if you have y as a function of x. So here's your general formula for curvature, and then if you're just talking about in the xy plane, y is a function of x, then you could use this formula. And that wouldn't be a hard thing to show. So if you had the special case of this one, where y was a function of x, you could do a little algebra and show that that is equivalent. Those are equivalent. Okay, so here's a nice exercise, and then it gives us a nice result, something important. We want to find the curvature of a circle with radius A. Find the curvature of a circle with radius A. So that's in R2. Okay, so that's in R2. Would doing that be a matter of using this one, Exhibit A, or Exhibit B? All right, so we want the curvature of a circle with radius A. So use Exhibit A or use Exhibit B. What do you think? Go ahead. Right, a circle is not nicely shown as a function of x. Y as a function of x, right? You'd have to have two. You'd have to have the top and the bottom. Well, then that's getting complicated. So we want to use this one. We want to use this one. So what do we need first? We need r. So first we need r sub t for a circle. We need the vector function for a circle in R2 with radius A. And then we'll take it from there, and we'll figure out what the curvature is by following the formula. So that is your task. So anybody get 1 over A before I did? About a quarter of you? Okay, good. And then those who aren't, if you're done, if you're working on the algebra, still you can work it out. If you're done, then ask, why does that make sense? Think about, why does this make sense? Okay, so keep working. Either you're finishing up the algebra or you're contemplating. So a really small circle. What about the curvature? super high, right? You're twisting, you're turning really fast. It's really tight twisting, right? That makes sense, right? So if you have a really small radius, then this number will be big. If you have a really big radius, then how about the curving? Right? So these particle accelerators, right? They really what they want is to accelerate particles in a straight line. But they have to build it as a circle. So how big of a circle do they build? The bigger the better, right? Like, so they build these gigantic circles, right? So that at the point of impact, it's like straight, like they're colliding those particles. So they get them going really fast, right? So the bigger the circle, the lower the curvature. Questions on this? Okay, so then let's look at this. Let's bring this together with an oscillating circle. So let's look at just x squared, and so we want to write, no, bad. Okay, there we go. X squared. So so here we go. So where's the curvature the least? Or sorry, the greatest? Where's the curvature the greatest? So then what about the radius? Smallest, right? Because 1 over. So whatever the curvature is, whatever the radius is, the curvature is 1 over that value. So what does it look like here? Let's get exactly n equals 0. Okay, so when n equals 0, what is the radius? So just based on the picture, can you tell me what the curvature is at n equals 0? What is the curvature? Radius is 1/2, curvature 2, right? Curvature 2. So let's write the equation of the circle. Can we write the equation of the osculating circle? So what is the oscillating circle? It's the circle tangent to the curve with the same curvature as the curve, right? So here I am at the point 1, 1. On y equals x squared. And that has a certain curvature there. And so now we're taking the circle with the same curvature and tangent at that point. That's called the osculating circle. So just for a moment, that y equals x squared has the same curvature as this particular circle, and based on the point of tangency, there is one equation of that circle. So the question is, can we write the equation of that circle? We've got all the things we need. So we know that the radius of that circle is going to be 1 over the curvature at 1, right? So we need to get the curvature at 1. And then what about how are we going to find where the center is? We're going to find where the center is. So we got this point. So where's the center in relation to this point? William. He wants the normal vector. So the direction of the normal vector, which has magnitude what? What's the normal vector? Because I'm holding up a 1, it's 1. Okay, and then so we got the normal vector is going to have magnitude of 1, pointing. So maybe like toward the center. So it's going to be pointing right to the center. So then we're going to find the normal vector, and then do what? Magnify it by the radius, and then get that ending point, right? So we'll get the vector in the direction of n with magnitude of the radius, and then figure out where the final destination would take you if you took that vector like that. So I want you to take a few minutes and think about how to get this vector n. I don't want you to figure out, so we don't want to figure out n of t. Don't find that. I want you to use something more quick and resourceful. What's a quick and resourceful way to figure out exactly what this n of 1 is? So don't find the whole function n of t, just find n of 1 based on your knowledge of calculus and vector. You have a good background in vectors, good background in calculus, so we should be able to devise a scheme to come up with n of 1 in an easy way, or in an easier way than finding the whole n function. Put your heads together. And then what about finding the curvature? What's going to be the most efficient way of finding the curvature? Plug in 1 to what? Right, which one? Which formula? Yeah. The second one, right? So now we can use, this is a great, now you can use the f of x, y equals f of x formula for curvature. You're going to plug in 1 to get the curvature, figure out what the normal vector is at 1, find the center. What am I showing you by the green line? What am I showing you by the green line? Yeah, the tangent line. So rate of change, right? So, or the direction of t, right? The direction of t. So tell me about that. So what's the key feature do we need to know? Do we need to know the y-intercept? No. What are we interested in that green line? Rate of change, right? The rate of change. Rate of change is 2. So that means for every 1 unit in x, we go 2 units up. So t is basically that. T of 1 is basically for every, what, 1 unit we go over, we go 2 units up, but what? Is that right? Is that what t is? That's the direction and the magnitude of that. So divided by 5. So using rate of change. The rate of change of y with respect to x is 2. So that means for every 1 you go over, oh, that's the x component of the vector, you would go up 2. And then to actually be the unit tangent, it would be divided by the magnitude. So 1 over radical 5, 2 over radical 5. Now, can you get n from there? Go. Keep going. Can you get n from there? Do it. We've done this before. We've done this little trick before, right? So there's your t. Questions on t? Do you see my logic there, my reasoning? So now you do n, and then try to find the center. A little bit more orthogonal. Yes, a little bit more orthogonal. I'll do it. Okay, so what's the x component of n going to be, first of all? The x component will be negative, and the y component will be positive. And then we need the dot product to be 0. Okay, so n of 1 is going to be negative something, positive something. So is it going to be 1 to 2 again? It's orthogonal. So is it going to be 1 this way and then 2 up, like t was? No, other way around, right? So we need 2 this way and 1 up, right? It's because if you're orthogonal like that and dot product needs to be 0, then really we're going up half as much. Here we're going up 2 times for every 1 in x. Here we're going up half as much, right? So it's going to be 2 over radical 5, negative 2 over radical 5, and positive 1 over radical 5. And you can check that by taking the dot product. So negative 2 over 5 plus positive 2 over 5. So you see how the rise and run flip, right? The rise and run flip, and we got to have a negative x component and a positive y component. And then what are we going to do now? So we're going to start at 1, 1, and we're going to go, how far? What'd you guys get for the curvature? 2 over square root of 125. You can work that out later. Therefore, the radius is square root of 125 over 2. And we're going to go that far in the direction of n. starting from 1, 1. So the x-coordinate will be what? 1 plus what? Radical 125 over 2 times negative 2 radical 5, right? So times the distance Yeah, so I'm doing it all at once. If you want to find this vector first, it won't have the plus 1 on it, okay? Find this vector first, it'll just be the 125 over 2 times negative 2 over radical 5. So that's the magnified n, and you're going to take that change in x plus the original x to get the point, right? This is an ordered pair now. This is not a vector. And then 1 plus the change in y, which would be the magnitude times the change of the unit vector. So what I'm putting in red is this is the magnified vector, right? That's the vector, n times the radius. What I put in red, that's n times the radius. And then you're going to take the x-coordinate 1 and add that change according to the vector. And then the y-coordinate 1 and add that change according to the vector. And so let's turn off that and put in our circle here. So what's the, I know, I'm so bored too. Okay, so here we go. X minus, what's the center? Anyone got a simplified version of that? 1 plus 1 minus 4? Yeah, 1 minus 5. Is that right? Plus y minus 6 equals that thing squared. So is that 125 over 4? Oh, I hope this works. Is that what we think? Moment of truth? Not right. What happened? My y is wrong. Why is my y wrong? It's not 6. 7 over 2? This is I'll take your word for it. Like that? Are we good now? Phew. Got it. Okay, did I lose you? If I lost you, ask. It's okay to ask if I lost you somewhere. I'm much more interested in you forming this kind of reasoning and problem solving than being able to do these long algebraic processes to find n of t or b of t, okay? This is knowing your way around curves, vectors, derivatives. That's kind of what I'd much rather see you develop your skills in. Please ask if I lost you. I'm begging you. I know someone has a question. Yes, please. Sure. Okay, so did you see how we got the t? We said the rate of change at 1, 1 was basically for every 1, the rate of change is 2, so for every 1 you go up 2. And so that's a change of x of 1 and change of y of 2, but then we made it a unit vector. Is that good? All right, so then if we have that, if this is 2 to 1, then what will this be? Orthogonal to it, right? So this 1 to 2 like this, then what will this be? In order to be orthogonal, then the dot product has to be 0. So this would have to be what? -2, 4, and then +1, like this. Do you see how, if you see the orientation of it, you see just the components are flipped. The magnitude of the components are flipped. This is 1 over and 2 up. Well, this is 2 over and 1 up. And you can see that if you do the product of the x's, you get -2. Product of the y's, you get 2. And so you get that orthogonality, dot product of 0. But then we need to make that a unit vector too. So -2 over radical 5. Is it better? Thank you.
This same trick does not work in 3D.
Right. Don't try this in R3. Leave that to the professionals.
How would we do that if we were doing it in R3?
So in R3, you would need more information, or you would need to have your n function and plug in the value. So this is kind of a trick that just works in R2 simply. So in R3, you'd have to have more information that would give you clues about the direction they're going. Like for instance, if it was a curve that was in a plane, like a planar curve, like the y coordinate was always 4, then you're just dealing with x and z, and you could do the same thing with x and z. Does that make sense? But if you're really truly moving through space in all 3 coordinates, this isn't going to be very efficient or practical. You need more information about the point you have in question. Okay, good questions. Any other questions? Okay, so let's talk about acceleration. So I showed you, when I showed you the cool curve with the one loop to loop, and we saw that acceleration vector was just kind of all over the place, right? Really, there was no rhyme or reason about where that acceleration vector was at any given time. So that's because there's 2 components to acceleration. So here's the setup. If r is position, then the second derivative is acceleration. So this r double prime vector is this one that we saw that was just kind of like flying in the wind. It didn't really ever seem to have a magnitude that made sense or a direction that made sense. It just was kind of all over. And the reason for that is that acceleration there's 2 phenomena with acceleration. There's 2 types of acceleration. There's speeding up and slowing down, the one you're most used to, right? The car is accelerating, you're flooring it, or you're jamming on the brakes. Okay, so what is that relative to r? What direction is that in? Speeding up or slowing down will have to do with what direction. So you should be thinking either r first derivative or t, right? First derivative or t. T is just the unit. So in the direction of t, that's the speeding up, slowing down part. Then there's a separate type of acceleration due to just turning. When you're turning, you're actually accelerating. Which direction are you accelerating when you're turning? In the direction of n. When you're turning, even if you're going at a constant speed, when you're turning, you're actually accelerating. You're accelerating towards the center of turning, like the center of the osculating circle. So when we take this r double prime vector that doesn't seem to have, you can't really see the meaning, and break it up into these 2 components, then things make sense because we're separating out the particular acceleration for speeding up and slowing down and the particular acceleration for turning. Okay, so this is what we're after. We want to rewrite r double prime as a tangential component and a normal component. And the tangential component is the speeding up, slowing down, and the normal component is acceleration due to turning. So notice, those are scalar functions, right? Those are scalar functions. Those change themselves with t. As time goes by, your amount of speeding up and slowing down changes. So it's a function, but it's not a vector function, it's a scalar function. And then as t increases, your acceleration due to turning changes. But again, that's a scalar. So then if we want r double prime, the acceleration vector, we take each of those and multiply them to get them in the right direction by their unit by their unit vectors in the right direction. Okay, so we can determine these two. We want a sub t and a sub n by taking the derivative of r prime, right? So r prime is our, what is that again? If r is position, that's our velocity. By taking the derivative of velocity, this kind of opens up these, gives us these things that we want. So that means that r double prime is the derivative of the velocity vector. That's where we're going with this. And we can rewrite velocity as speed times the unit tangent. Should make perfect sense, right? Speed is what? The magnitude. This is the same as, this is our magnitude of velocity, right? Let's try that again. So what is that? That's the speed function, right? So that would be magnitude of velocity. So if we just take the speed out and then multiply it back by the unit tangent, we get the velocity, right? So if we're going to take the derivative of that, we got two functions of t, and we take the derivative with respect to t, what do we need to use? We have a scalar function of t times a vector function of t, but they're both functions of t, and we're taking the derivative with respect to t. So we need Mark got it. Product rule, right? This is going to be the product rule, the derivative of two functions of t. We know the product rule. So here's what it looks like. Derivative of the first times the second plus the first times the derivative of the second. Okay, so we're pretty much done. We've just pretty much got a sub t, right? So this is what? If this is the speed, if vt is the speed, well then the derivative of speed is just going to be how much we're speeding up or slowing down. That's a sub t. We're done with that. That's our a sub t function. Here, this is different, right? So we gotta do some work here to get something times n, right? We don't have that. But we're pretty much done with the speeding up or slowing down part. It's just going to be the derivative of the speed. That's our a sub t function. Okay, so now to work on the second part, we gotta, this is kind of a parenthesis. This is a parenthesis. Here's a couple things we know. We know that the curvature is magnitude of t prime over r prime t. And n is the unitized derivative of t. So that's from, and we're going to use both those two things to what? We're going to rewrite this. So using those two formulas to rewrite t prime. So first t prime is going to be nt times that. And then this is going to be curvature times that. So still in parentheses. So putting those two together, we get that t prime, so here, t prime is, again, this times this. That's right there. And now, what is that? That is this times this. So altogether, curvature times magnitude of r prime times n. And so we can substitute that. Oh, I hate that. Coming back. All right, so we can substitute that in for there. So using our formulas for n and curvature from before, we can kind of rearrange those, and we can replace t prime with curvature times magnitude of the velocity times nt. Okay, so when we do that, we get this. So notice, magnitude of velocity, right there, what is that the same as? Magnitude of velocity is speed, is this again. So this right here, the magnitude of r prime, is also v of t, so we got v of t squared. So we got v of t squared, those two, times curvature times n. And we got it. So now we have a sub n as well. So a sub t is just the derivative of the speed function, or v prime of t. And a sub n is the speed squared times the curvature. So what is that again? This is the acceleration due to turning. So does it make sense that it would be directly proportional to, not directly proportional, but in direct relationship with the speed? So the faster you're going around a turn, the more your acceleration due to turning is. And then the tighter your turn is, right? The higher your curvature is, the more the acceleration. But the speed has the higher influence on it. So you're going around some curve. If it's a tight curve, you're going to have a high acceleration due to turning. And then your speed is going to, if you have a high speed, that's going to really give you a high acceleration due to turning. Okay, good so far? Okay, now there's an alternate way to calculate these. So, which do you use? You use whatever's most convenient at the time in the problem. Whatever will get you the values fastest. So, you know, maybe finding this curvature would be really difficult, right? So maybe that's really hairy, so you want to do this instead. So let's talk about acceleration due to speeding up and slowing down. Again, if you're talking about comparing r prime to r double prime, what would that be a matter of r prime and r double prime if we want how fast we're speeding up or slowing down in the direction of motion? So if it's with r double prime and r prime would be what thing are we going to have there? So this is at now in the direction of motion, speeding up and slowing down. You can't. I've got two vector functions there. I'm multiplying together. How am I going to multiply them together? Which kind? Cross or dot? This is cross or product. So this is a sub t due to speeding up and slowing down. Dot, right? We want the product of those two, and as much as they're in the same direction, meaning in the direction of r prime. We want dot product, right? We want dot product. And then what about normal? That's like curvature, right? So for the normal vector, it's the same idea as curvature, matter of cross product, right? Cross product. Because r prime is the direction, it's like the direction of t. So we want them in as much as they're orthogonal, right? Or their product in as much as they're orthogonal, because we want them in the direction of n. So two different ways to calculate AT and two different ways to calculate AN. So this is a lot more kind of meaningful way to look at the r double prime vector. Because when you put it all together and just look at the three components of r double prime, like we saw in that example, remember, it's just kind of that a vector was just kind of all over the place, and there's no rhyme or reason to it. But it's when you separate it into the two types of acceleration that it really we could look at an animation and really make sense of, okay, this is how much is speeding up, slowing down, and amount of turning. So I need an animation that shows that, and so that we can really analyze that. So I'll work on that. Okay, does it make sense? So we're writing that second derivative in a new way, reflecting the two individual types of acceleration. And the scalar magnitudes of each of those, you've got two ways to calculate it. AT, either this way or this way. A sub n, either this way or this way. Any questions on that? Okay, so we want to change gears. So this is we're kind of done with space curves for now, and motion in space, or motion in the plane. Any questions on that stuff? So I don't have a fancy slide for you for the next section, but we're going to work on multivariable functions. I guess it could be. I'll just build the slide as I go, okay? Faster anyway. Okay, multivariable functions. Okay, so most functions today in your career have been of the form what? Single variable, real valued functions. So what does all that mean? Single variable refers to what? X. No, so single variable means one input, one dependent variable. One dependent variable, single variable. So that's one independent variable. Did I say dependent? Sorry, I should have said independent. Real valued. And what does that refer to? Your dependent variable is a single scalar. It's a single real value. One. So y equals f of x is a single variable, real valued function. So what would you call these vector functions we just got done with? How would you describe those vector functions we just got done with? So R of t. So how would you describe that if you're using the same? Anyone want to get a shot? Is it single variable? Try again. Is it single variable? Yeah, sure. What does single variable refer to? one independent variable. That's a single variable function. Is it real valued? 0 for 2. Single variable refers to the independent variable. That's what we've got. Do we have one real value coming out of this? No, what do we have? A vector, right? We have a vector. So this is single variable vector valued function. Why? Because one single variable t, and then the thing that's coming out for every t, what do we get? We get a vector. We don't get a real number anymore. We get a vector, and that goes for whether it's an R2 vector or R3 vector. Doesn't matter. That's a single variable vector valued function. Okay. So now what we're going to do is multivariable real valued functions. So tell the person next to you, what is that? So now we're going to do so what is a multivariable real valued function? Talk to the person next to you. Go. What would that be? What is a multivariable real valued function? Go.
So like single value, like x multivariable, right? Yeah, that's a good way to talk about it. It's a single variable. Like y
So think of R3. What would the most basic one of those be in the R3 system? Was it? Someone said it. Okay, I think you got it. So write it in. What would it be in this form here? Would it be like this? Right. Example, and the example we're going to be working on, z is function of x and y. So that's an example of a multivariable real valued function, because you could have more. Multivariable now means you could have two or more independent variables. But in R3, this makes the most sense, right? So you've got two independent variables, x and y. And then based on the function, you're going to take a value of each of those, and the function is going to tell us then what the corresponding value of z is. Okay, so for example, wave height function. An unfortunate reality at this time of year, right? There's another one coming. Do you know that? There's another one coming towards the Caribbean. All right, another hurricane. So we could say H. What am I trying to say? H equals, say, G of R T. So H would be wave height wave height is a function of both wind speed and duration of time. Okay, so if you have still water and a big wind comes up and starts blowing really hard, you're not going to have big waves right away, right? But if that really strong wind blows the longer that strong wind blows, the more the waves start to build. All right? So the amount of speed is going to influence the wave height, and then the length of time that the wind is blowing at that speed is going to affect the wave height. So you see that wave height is really a function of two different variables. Two different variables. That's what we're talking about here. Okay, so there's different representations. The first is the formula. Right? So function. So z equals. So what would be if z is a function of x and y? What's an example of a rule that would be where z is a function of x and y? Yeah. So and we know what that is, right? What is x squared? What is that? Oh, don't say circle, please. It's not a double cone, please. Paraboloid, right? This is our paraboloid. So the first type of representation is formula. Or function rule, function definition. Okay. Second would be a graph in R3. So where does the domain come from? And then where is the range? And what kind of thing will you get? Where does the domain come from? Right, where is that? The xy plane would be where our domain of this function is. So for what ordered pairs x and y do we get a valid z? In this case, what would be the domain? What for all real squared, right? So all ordered pairs x and y, the whole xy plane would be the domain of this because it gives a valid z. Okay? And then what kind of thing do you get? Then for every x and y, you get a particular z. So then if you put all those together, what kind of graph do you get? Do you get a space curve? I should have written f of xy. Surface, right? We're going to get a surface. If you continuously join all those points where you get a z from every particular x and y, you're going to get a surface. And we know exactly what this surface looks like, right? It's our paraboloid opening on the positive z-axis. Right? Okay, next one is, remember doing traces? So when you have traces that are particularly z equals, these are called contours or a contoured map. So traces where z equals k for various k's. Remember doing traces? So in particular, you want to do traces for z values. And then you're going to get what's called a contour map. So it's like taking all those z traces and putting them in the xy plane, and you get a contour map. So this is kind of like what's this called? Like for hikers and what is it? Topographical map. Right? It's exactly what it is. A topographical map is the same as a contour map. You take different traces at different levels of z, and then you flatten those all straight down onto the xy plane. So what would it be for our paraboloid? What would they be? Concentric circles. Yeah. Would they be equally spaced or not equally spaced for the paraboloid? Equally spaced or not? For if I take if I took like integer values of z, are they going to be equally spaced or not? No. Are they going to get, as you get bigger, are they going to get closer together or further apart? Closer together, right? They're going to get closer together, right? Because going up, you have going up z, you have less change in radius as this thing gets bigger. So those are going to get closer and closer together, showing when the contour lines are close together, you have the surface is more steep. And when the contour lines are further apart, it's more shallow, like in the middle. So what would have equally spaced circles? What kind of surface would have equally spaced contour lines? The cone. The cone would have the equally spaced. Okay, and then the last double curves formula. Oh, a table, right? So you could have a table of x and y values, and then inside the table will tell you the particular z for each corresponding x and y. So I'll just write down table. Number 4 is a table of values. Is another representation of this. Okay, so then 0 for our particular function we're looking at, that paraboloid, 0, 0 gives 0, 0, 1 gives 1, 0, 2 gives 4. 1, 1 gives 2. What does 1, 2 give? 5. 1, 2 gives 5, and 2, 2 gives 8. So that's an example, a table of values of f of xy equals x squared plus y squared. So those are the 4 primary, sorry, we're late, I'll give you back time another day. Those are the 4 primary representations of a multivariable function, c is a function of x and y. Hold on, we didn't do anything on them, right? Save your pink sheet for Thursday. Just bring it back Thursday. See ya.
See you later.
Extra? Thanks. Do you have a question, Adam?
I gotta go.
Okay.
So I might
Sorry. Thank you.
If you possibly check what the ones you discarded was mine, just to be sure.
Discarded what?
For the submitted homework today.
I didn't discard any.
Oh, okay.
I just kind of handed. I didn't discard it. Is this it?
No.
No. This was the one.
Much.
Yeah. No, I didn't discard any. I just was handing it back to students to fix it.